our company started.
All right, so this is about the development of what we call the V2 rocket, which was the world's first ballistic missile developed by the German military between 1941 and 1942, 1944, really. And this is the sort of a cutaway of the V2 missile, the plastic model of it, what it looked like from the outside. And it was never of great benefit to the German war effort because of the fact that it was never very accurate. It just couldn't hit targets with it. I mean, some of the flights missed their target by 15 miles, and that's just not accurate enough to fight a war. But it influenced technology in the 20th century in a major way because they basically invented the rocket. I mean, there were rockets before this, nothing like the V2. And this had its own automated guidance system. It was much larger than any rocket before then. And they had to figure out a lot of technical issues in order to make this thing work. So it really was a major influence on the 20th century, even though it didn't do the German military that much good. Now, in order to understand the military significance of rockets, it helps to understand how they derive their impulse to move forward. That top little cartoon shows a car, and there's two red arrows, and that's supposed to depict the fact that when a car drives down the road, what's happening is the wheels, the driving wheels, are pushing rearward against the road. And according to Newton's third law of motion, the road is pushing forward in an equal and opposite way. And that's why your car moves down the road. That airplane, the propeller, pushes rearward on the air, spinning, turning through it, and the air pushes forward in an equal and opposite way, so the airplane moves forward. There's a jet plane, similar to a propeller plane. Air is drawn in the engine, and there's a fan back here, which pushes the air rearward very powerfully, and the air pushes forward in an equal and opposite way, according to the third law. Now, here's a rocket. It's similar to a jet in that hot gas is expelled rearward, pushed rearward, and the hot gas pushes forward in an equal and opposite way. The difference is that all that gas, instead of coming into the engine from out in front of the vehicle, it comes from onboard the vehicle. So all that impulsive medium, that gas, comes from onboard the vehicle. That makes it a very different kind of machine. It's difficult to engineer because all that impulsive medium has to be on board when the thing takes off, so it can be extremely heavy. And of course the engine has to be very powerful to carry that stuff up. But there are two major advantages to rockets over these other things. One is they can operate at a much higher speed. The fastest jet in the world travels a few thousand miles an hour. At speeds higher than that, air moving into the front of the engine rips the engine apart. But rockets can travel at speeds a lot higher than that. And because it carries all this impulsive medium with it, it can operate in a vacuum. The only kind of engine that can operate in a vacuum. So a missile launched from the ground can fly up above the Earth's atmosphere and drift hundreds or even thousands of miles downrange, re-enter the atmosphere, and when it comes down to its target, it's moving at a speed that makes it pretty well unstoppable. And that's, in fact, what the V2 did. It flew up into space and came down on its target. So those are two big advantages in what they're
Sometimes take a little bit down.
Right. This is basically how a rocket engine works. Two components of the propellant called the fuel and the oxidizer, which in the case of the V2 were alcohol, ethanol was the fuel, and the oxidizer was liquid oxygen. Those are pumped into the combustion chamber of the engine, and where they react chemically, combusted, and then that hot gas that resulted went out the expansion chamber of the engine and accelerate very fast in that direction. These pumps have to be extremely powerful in order to pump that fluid in there because it has to be pumped at a very high rate. And when this is running, the pressure of this chamber can be 1,000 psi. So you got to pump a large quantity of fluid into the high pressure. So this is a very difficult thing to engineer. Conceptually very simple, but rocket science really is. It takes as much brain power as it sounds like.
Well, images usually, yeah, it's just images, it'll take a while to load.
Okay. I think it's the
I didn't click on that, right?
treaty of Versailles. I think the next picture shows the signing of the Treaty of Versailles in 1919. It ended World War I.
So, basically, in the combustion chamber, that's where the two elements meet at to cause explosion.
Yeah, they react chemically. Ethanol, alcohol burns, right? And what's happening when alcohol burns is it's chemically reacting with oxygen to form what I guess CO2 and H2O mostly. And that reaction is exothermic. It produces a lot of energy. So that's what's going on in the combustion chamber. But it was very high rate. What it took, didn't know how much propellant was there on board. It took a little over a minute to burn all the propellant on the V2, and there was a ton and a half of propellant, something like that. Very, very fast. This photograph is taken in 1919. The signing of the Treaty of Versailles that ended World War I. And Germany lost World War I, and so the Treaty of Versailles put a lot of restrictions on what they could do with their military. And one of them was it restricted Germany from having armed aircraft, which World War I made obvious the potential of aircraft in warfare. So the German military saw this as a bad restriction. And so they looked for ways to have airborne weapons without building armed aircraft. But the Treaty of Versailles said nothing about rockets. So they decided to develop rockets, partly because it was a way to have airborne weapon systems without violating the Treaty of Versailles. Go ahead. And this is a German guy that was central to the development of rocketry in Germany. His name is Hermann Oberth, and he has had a lifelong dream of space travel. He wanted to go to other planets, to the moon and the other planets. He had read, when he was a kid, he had read the novels of Jules Verne, and the ones that he liked the most were the ones about space travel. And he apparently had one of them almost memorized. But that started him on a lifelong quest to explore space, to fly in space. And he was, I guess, a pretty smart kid and realized that you couldn't fly in space the way Jules Verne suggested, which was to be fired out of a huge cannon. But so he became an engineer and realized that rocket engines were about the only way to fly in space. They carry their own impulsive medium, and so they can fly in a vacuum, which space is a vacuum, so you can move around in space with that. In the 20s, he wrote a book. He published a book in 1923 called The Rocket into Interplanetary Space, which was about the use of rocket engines for space travel. And this inspired more people, especially in Germany, including a very young guy named Werner von Braun. Has anybody ever heard that name before?
It sounds familiar.
He's probably the most famous rocket engineer of the 20th century. He became centrally involved in the development of the V-2 missile and eventually came to the United States and headed the development of the missile program here, and then headed the development of the rockets that were used during the Apollo missions to go to the moon. He became very famous here as a result of that. And he read this book when he was a kid, and this really made him want to go into rocketry. So he became an engineer because of this book. And this is this is a photograph taken in 29. Oberth and some other people formed a club called the Society for Spaceship Travel. That is in Germany, the VFR, and this is Oberth in the middle. And their whole deal was to build rockets, to develop rocket technology for the ultimate dream of flying in space. Rockets existed in some form at the time, but they really had to move a lot farther forward in order to fly in space with them. And that's what these people dreamed of doing. And this is Werner von Braun. He was actually in college at the time studying engineering. Let's see. One of the ways that this group, and there were several hundred people in this group, and one of the ways that they raised money to build these rockets of theirs was to do public exhibitions of the flight of their little rockets. And at one of these exhibitions in, I believe, 1930, a couple of members of the German army showed up to watch the exhibition and approached the members of the VFR afterwards and said, we'd like to develop a weapon with this technology. Would you be interested in helping? And eventually, a couple of members of the VFR became centrally involved in the development of the V-2 missile. The German military was partly inspired, by the way, by the work of Robert Goddard in the United States. Robert Goddard was one of the few people in the United States that was interested in developing rockets, and he had flying rockets in the 20s, around the same time that the VFR were building them.
Well, if it's an image that I'd like to take a photo of.
Oh, yeah. Oh, it's Coomer's story. So the military effort to develop a missile began in 1931 at Kummersdorf, which was a place in Germany where innovative weapon systems were researched and developed. And they developed a sequence of increasingly large rockets. They called them the A1, A2, A3, A4. And they were eventually going to be up to A12, but they only got as far as A4, which we now call the B2. And this is a flight of the A3 in 1937, which was a pretty large thing. Now let's see. There are three critical technologies to flying a missile that you have to develop in order to make the thing work. One is the propulsion system. The rocket engines that the VFR were using had a thrust pushing forth a few tens of pounds. But they had to develop a propulsion system that had thousands of times more thrust than that in order to carry an explosive warhead that was large enough to be of practical military value. And so the propulsion system had to be vastly increased in size. So that was one major hurdle they had to overcome. Another was how to control the rocket in flight. You have to be able to guide its flight, right? In order for it to go and hit some sort of target somewhere. How do you do that? And then, assuming you can control it in flight, there's got to be some sort of artificial brain on board to use those controls to take it to the target that it's supposed to hit. So those are the three main systems. You can go ahead. This first slide shows the engine of the V2. Okay, here's the engine of the V2. So here's a big spherical thing is the combustion chamber. That's where the propellant got pumped into and where it combusted and produces hot gas, which moved into this expansion chamber here and accelerated that way to about 2,000 meters per second. So this is the A4 engine. This is the engine on that thing. Okay, go ahead. The next one shows a little diagram of the plumbing involved in the V2 engine. And you can see there's some complexity to that. The purple tank is the fuel, ethanol. It's actually ethanol mixed with water. I'm not sure what the water is, but the red is liquid oxygen. And let's see, green is compressed air. The compressed air forced the propellant out of those tanks and into the pumps. So in order to get it running at a high enough speed to feed the pumps properly. They use compressed air. And then the pumps would pump it into the high pressure running combustion chamber. So the pumps had to be very, very powerful. And that was actually powered by a separate system, which involved, sodium permanganate and hydrogen peroxide. Those two things react together and produce a lot of energy. So that reaction ran a turbine, which ran the pump, which pumps propellant into the combustion chamber. It has to be a very powerful system to pump all that fluid into such a high pressure. One of the interesting stories is that the engineers actually didn't have to develop the pump for these rockets because there happened to be a pump they could use off the shelf that had been developed for fire engines. You know, they had to pump water at really high pressures and high rates on fire engines, and this was a turbo pump that was developed for that purpose. So that's one system they didn't have to invent themselves. And this next graph, I think, shows the progression of engine thrust through the development from 1931 up until 1942 when the engine was ready for the missile. It increased from, it's a logarithmic scale, here's 100 pounds, 1,000 pounds, 10,000, 100,000. So they started out with less than 100 pounds of thrust and wound up with the V2 engine, which had 55,000 pounds of thrust, enough to carry this huge thing hundreds of miles. Then what about the controlling the rocket in flight? So these fins provide stabilization as the rocket flies through the air. The fins keep it pointed forward, but you, of course, have to guide it in flight because your target might be a building that's 180 miles away. You have to somehow direct it to get there. And you can see the control system. This is the back end of the V2, looking like this. And I think this is actually a captured V2 that landed in Antwerp and didn't explode. This right here, in the end of the fin, there's a little control surface that acts as like a flap. This is the way airplanes control themselves in flight. You move these control surfaces and it changes the way the air moves across the wing, and you can guide your direction in flight. Now, airplanes move at pretty constant speed, but rockets have a much larger range of speed. When they take off, the V2 at least took off vertically from a standing start. So it was moving hardly not at all, very heavy at that point, so it took a lot of control to control its direction. And then they accelerate up to supersonic speed. So they have huge range of speed over which they operate. And then they fly into a vacuum. And in a vacuum, this control surface is not going to do you any good because there's no air moving across the fins anymore. So there was another control system. These vanes were actually immersed in the engine, in the hot gas coming out of the rocket engine. And they were controlled, they could change their orientation like that, controlled by the control system on board. And so that would actually deflect the rocket exhaust, and it could be controlled that way. Okay, let's see, I think the next is a photograph of that control vane system. And you can see the way it's connected to the bottom of the engine. And you can see here's the control vane, and it's on like a sort of axle here, and it can reorient itself like that, and as the exhaust goes past, it redirects. You can see right here is a lever that went to a crank, and that is what turned the vane. And this next thing is a photograph of a static test of this system. They bolted down the engine and ran it and to see how the thing works. And so here's kind of hard to see, it's an old photograph. But here's one of the vanes, here's the hot gas roaring out of the engine. And it's roaring past these vanes when they were testing it here. Now, what about guidance? So this is the way the thing is controlled, but something's got to do the controlling of these control surfaces to guide the thing to the right place. There's no one on board because it's going to blow up at the end, right? So how do you guide this thing? Well, there has to be some sort of system on board, like a computer, that can make input for these control surfaces to tell it where to go. Now, it has to take itself to a particular target, which means it has to know where it is in order to know which direction to go where it needs to go, right? So part of the guidance system is there to measure where the rocket is in space, and what direction it's moving, what direction it's pointing. And part of that is these gyroscopes. Inside these cans here are spinning flywheels, and then this is, let's see, okay, that's on an axis. You can hardly see it here, but that is swiveled on an axis that goes this way. So that whole can with the spinning gyroscope can be swiveled this way. And then this whole frame that that's swiveling on is on an axis, so it can be swiveled this way. So it can spin that way and that way. It is complete freedom to move in any direction, right? But when a flywheel is spinning, the fact that it's spinning gives it a resistance to having the orientation of its axis changed like that. So if you pick up this whole frame around it and move it, because of the fact that it's sitting on those free axis gimbals like that, the flywheel will remain in its same orientation even though you move that framework around it. So the advantage of doing that on board a rocket is that this flywheel will maintain its orientation even though the rocket is moving all around and changing its direction. So that gives the rocket a rotational reference frame, so that it knows, with respect to that reference frame, it knows which way it's pointed. Does that make sense? So that thing is not turning, so it knows, okay, that's the motionless reference frame. Since I'm tilted this much with respect to that, my angle must be. So that tells the rocket where it's pointed, and one of these gyroscopes is meant to tell it this direction, one of them is meant to tell it that direction. So that's what that's for. The next thing is what's called an accelerometer. An accelerometer measures acceleration. So when it's accelerating, acceleration means the rate of change of your speed, right? When this thing takes off, everything on board feels heavier, right? And the sense of heaviness can be used to determine how fast it's accelerating. The faster the thing accelerates, the heavier things on board feel. So this is the way the rate of acceleration is detected by a thing called an accelerometer. And this actually employs another gyroscope. The way it measured acceleration was with another gyroscope. So if you know those two things, if you know which direction you're pointed in space and at every moment in time, and you know your acceleration every moment in time, you can sort of see how, if you take off here, the distance between those points tells you how fast you're going, right? And the orientation of line tells you the direction that you're going. If you can monitor the direction that you're pointed in space plus the rate of your acceleration, you can use that to mathematically calculate where you are, right? And so that's how the guidance system was able to know where it was at any given point in its flight. Okay, go ahead. But then, using that data, something has to use that data to know where it is and thus to know which way to point the control system to reach the target. And that was the job of the guidance computer. And it was a fully electronic computer. And this is 1944 when the first one flew. Don't think of electronic computers going back that far, but it was a fully electronic computer invented specifically for the V2. These didn't exist before the war, but this was developed specifically for the V2. And it was an analog computer as opposed to a digital computer, which is what we use today. Now this, of course, didn't have a heck of a lot of computing capacity, but it was enough to take that data of position in space and speed and everything, and guide the rocket to its target. So it was quite an innovation in itself. There was an interesting factoid about this. The guy that invented it was named Holzer, Hoeltzer. Anybody recognize that name? You might recognize that name. There was a girl that swam for the U.S. in 2004, and it was Shannon Holzer, I think, as his granddaughter. She's from Huntsville. He moved to Huntsville after the war to develop rockets for NASA, and his granddaughter was an Olympic swimmer. And then in the front of the rocket is the warhead. It had a 1-ton warhead, so it's a pretty powerful warhead. It made a great big explosion when it got to its target. And because of the inaccuracy of the V2, these things exploded all over the place and killed quite a few people, mostly in Antwerp and in London. And it was sort of a terror weapon at the time because they landed all over the place, for one thing, and because they came in at speed greatly in excess of the speed of sound, so you didn't hear them coming. All of a sudden, it'd be this enormous explosion. So it terrorized the English people more than anything, but didn't really affect the war in Germany's favor.
What's actually inside of the warhead that causes it to explode?
That makes it explode? Some sort of detonator. I don't know how they work. It was electrically activated. I guess, I don't really know how it works. The electricity would somehow fire some sort of chemical detonator, something that would explode when you put electricity through it, and then that explosion set off the rest of the warhead. I don't really know how it worked. I know it was detonated electrically. That's what the wires were. So you can see the parts of the V2. Here's the propellant tank, fuel, and oxygen, which was about 3/4 of the liftoff weight of this thing. And then the plumbing of the fuel system, and here's the engine, the control thing, and the guidance system and the warhead on the top. And here you see the ribbing that made it structurally sound, and the skin made it aerodynamically slick to move through the air at super high speed. Yes, sir. And here's what a flight more or less looked like. It took off vertically from some place in continental Europe, and they fired them from a number of different places. But immediately off the ground, it started to flew over toward its target, and flew until it was nearly out of propellant, which was in the upper part of the atmosphere, where the atmosphere is very thin. And then it would drift out of the atmosphere and then tumble end over end aimlessly toward its target. And when it hit the atmosphere again, the fin would get it going nose first, and it would come into its target this way. Now, the only guidance took place in this part. After the engine cut off, there was no guidance, and so it had to be on the trajectory to hit the target at that point. One of the reasons it was not very accurate. It was very difficult to hit a target with this kind of a system. I guess they just didn't have the sophistication in their guidance system to have active guidance when it got to this point in the flight, so they could sort of like glide it in. I mean, that would have been possible, but once it was out of propellant, it was basically on a ballistic trajectory, which is what they call ballistic missiles. It was just like a shell fired out of the gun, but the guidance is just up to that point.
I was gonna wait for the end to ask this, but I think I just answered. I was gonna ask you earlier, when you were talking about the accelerometer, I'm wondering how that would have worked in a vacuum of space, but if all of the trajectory and whatnot took place before reaching that point, then I guess that...
Yeah, once the engine shut off, there was essentially no acceleration. But an accelerometer will work in space, because you don't need air for the acceleration to work. I was going to bring a demo, but I forgot if you hang a weight on a spring scale, it reads, the reading on it is the weight of the weight. And then if you pull it up, the reading is greater, right? Because you're measuring the weight of the weight plus the force that you're pulling it up with, right? That makes a crude accelerometer, and that would behave that way whether or not the air was mounted. Does that make sense?
Oh, okay.
So accelerometers work in space, and they're critical to guiding things like spacecraft in space. But yeah, you're right. After the engine cut off, that was the end of the control play. This is a photograph of German military brass, I guess, inspecting one of the production places for the V2. This is Werner von Braun. He's actually a member of the SS. I managed to find one photograph of him in his SS uniform. He never wanted to wear it, but somebody forced him to wear it when Himmler showed up to inspect the place where they're building the rocket. But that's good. Okay. This is the people that constructed these thousands of V2s that were used in combat. They used slave labor. They used people from concentration camps. And they were assembled underground in these mine shafts and things. And the conditions were very poor, and a lot of people died as a result of the conditions, and also a bombing attack of the Allies in an attempt to destroy the production of these missiles. So as many as 20,000 people died building these missiles after the production started and they started using them in combat. And the next is a picture of one of these underground production facilities, probably taken after the war when it was captured by the Allies. That's a nice picture. Yeah, so here's you can see the rock ceiling, and here's lots of V2 engines, railroad tracks for transporting things around. This is a big production operation because several thousand V2s were fired in combat, and these are pretty big items. Good. A1, A2, A3, A4. The A in there stands for aggregate. The whole original plan was to build a whole line of rockets, but they only got as far as the A4. But they were increasingly sophisticated rockets. And the A9 this is a cockpit. It was going to be a piloted missile, so it would have been much more accurate because it could have been flown by a pilot all the way nearly to the target. And then this huge thing was supposed to be like a first stage for the A9. Flip it in. This is what they wanted to do. This is like an artist's conception of a takeoff of an A9/A10. So you can see here's the big thing with the A9 tucked in its little compartment. So the A10 served as a first stage for the A9. In other words, the A9 was not running at this point. The bigger rocket would take it up, accelerate it, probably get it to the top of the atmosphere, and then the A9 would show that one. And this shows when the A10 had run out of propellant, and the A9 was flying on to its target. Staging rockets like this, so here's the spent A10 falling back to Earth. Staging rockets like this vastly increases their range, and that's how spaceflight is done now, is to go to the super high velocities that you need to reach to go into orbit around the Earth. They use rocket staging. And this could actually have hit targets anywhere in the world. Well, almost anywhere in the world. They could have hit targets in the United States with this. So this is one of the reasons why the Allies did bombing campaigns trying to stop the production of this. And this last frame, I'm sure they were surrendered. The V2 wasn't operational until the fall of '44. And then, of course, the war in Europe was over in the spring of 45. So it was only really used for about 6 months, but they still launched like 2,000 against Allied targets. And then the Allies invaded Europe and captured most of the material that was produced. A lot of rockets, a lot of information on the technology, and a whole bunch of the personnel that developed it. This is Werner von Braun, who he and 3 other engineers. This guy is Walter Dornberger. He was the head of the project from 31 until I think 43. And there were 2 other engineers. The staff, the engineering and technical staff, had dispersed into a couple of German towns. The SS wanted to collect them together and get them closer to Berlin to keep them from being captured. And von Braun and others were afraid that what they were going to do is, if there was any threat of their being captured, they would execute them to keep the technology from falling into the hands of the enemy. And, so von Braun actually convinced the SS head of the rocket program to let them disperse into the community where they were. And these 4 guys happened to bump into, when the Allies invaded, they happened to bump into an American private. And they surrendered to him. They were trying to avoid being caught by the Russians or by the SS because they were afraid of being killed by either one of them. But so they surrendered to the U.S. and a lot of these people eventually came to the United States and formed the core of the intellectual capability that started the U.S. rocket program and eventually developed the rockets that sent people to the moon in the late 60s. So the chief benefactor of this was probably the United States, because all that technology came to the United States and jump-started the development of the American missile program. It could be that the most significant thing about the rocket program was, besides that, but the most significant thing for World War II was the fact that it cost Germany billions of dollars to develop it. The scale of the effort was nearly equal in terms of the GNP of the country to the scale of the Manhattan Project in the United States to develop nuclear weapons. So it really drew a lot of resources out of German military spending, and probably did a war effort more harm than good, but it invented rocketry. That's it. Thank you.
Thank you.
Any questions?
So basically, Germany created the rocket, largely used it against them in World War II. So, I mean, what's like the most popular weapon today, besides the atomic bomb?
Well,
and didn't Germans invent that too?
no, actually that was developed in the U.S.
Okay.
So it was developed in the U.S. because the fear was that Germany would develop nuclear weapons and put them on their V-2 and send them overseas, And of course, that's eventually what missiles came to do. I mean, there are a lot of missiles used in the military today, but the biggest ones are the intercontinental ballistic missiles that are used to carry nuclear warheads, which, that system, intercontinental missiles with nuclear warheads, probably affected, of all technologies, they have affected the 20th century history more than anything else, because so many of them were produced by the U.S. and the Soviet Union, and really determined the relations between the 2 superpowers for most of the 20th century. So, I mean, that's an important point, that these eventually became used with nuclear weapons. That's really what made them so significant. So did I hear you say that they weren't used, this was not used against Germany, but it was captured at the end of the war. And American military took the technology back to the United States and used it to develop their own missile program.
Did these rockets have a sort of like a fail-safe, and then if something went wrong in flight, they could disarm the warhead, or was it a done deal once they?
I don't think so. I don't think they did. I'm not sure. That's a good question. I don't know. And because, you know, especially early on, there were a lot of failures, and they hit the ground and exploded.
Oh, okay.
You know, when these things crash, I mean, they're loaded with tons of propellant. Whenever they hit the ground, there's a lot of fire. But I don't know. That's a good question. I'm not sure there was any radio contact with the thing after it launched. It was programmed to go to a certain place and then on its way.
What was the range of the explosion?
Oh, yeah, good question. The range, maximum about 180 miles.
Whoa.
Yeah, so.
The explosion could go out?
Oh, no, no.
Oh, okay. Oh.
No.
Oh, okay, yeah.
The range of the rocket, yeah. Sorry. Yeah, it was at a one-ton warhead, which, I don't know how much destructive, let's see, if you had a one-ton warhead in here and it blew up, it would probably take out most of the end building. Yeah, you know, it destroyed whatever it hit, but unfortunately for the German military, it hit mostly out the country, you know, places where it didn't really do much damage. Every once in a while, they hit something important, and that was an success. And if it hit an urban area, people would be killed. But, you know, in order to have military importance, you got to hit what you want to hit. Is there any extra time? I actually have something that
We have maybe, yeah, we have about 10 minutes.
okay. I actually made out the original idea. I don't know if this is going to go across the window thing, but I made an Excel file that's sort of a simulation of the flight.
No, well, let me see if I can do the share thing.
Okay.
Share.
And it's interesting because when I made this little file, it's a numerical simulation of the flight of the V2. I put in all the parameters like the weight of the rocket, the weight of the propellant, the exhaust speed, and all this stuff. And it makes a simulation that's probably somewhat close to the way it really flew. And there's some of the results of the simulation are interesting because one of the things that they noticed when they were shooting these missiles in combat is when they re-entered the atmosphere, they were breaking up. They were coming apart before they hit the ground, and they didn't know why. And the simulation,
Wait a minute,
is it going to work?
well, yeah, why don't you get to the computer and go? Yes. So the online people should now see the entire desktop.
Oh, okay, great. Computer. Can I hear us?
Yes, then it's a wire.
Okay, so this is, I believe the edge simulation. Scale. Okay, so I was originally going to do this as a kind of a game, but it doesn't make a very exciting game. I mean, so what what you see there is the trajectory, and what you change, that number at 43 is the slew rate. This is not actually the way they guided the V2, but once it goes off the pad, it starts banking over, slewing over, and what you vary is the number of degrees per minute that it's changing its orientation. And that, of course, changes where it winds up, right? If I go right in 25, so then it goes on a steeper trajectory and comes down closer to the takeoff point. This box is when the propellant runs out. So on the real V2, they didn't really guide it this way. I mean, the slew rate was controlled by the computer. But what determined the range was where the engine cut off. They didn't actually let the propellant run out like they do in the simulation. It would shut off the engine at a certain point, and that would determine how far it would go. If it shut off down here, it would go as far. So that would determine the range. But the idea was you set the range of a target here, like 165 miles, and then you adjust this until you get 155 miles. Yeah, this is why it's not a very exciting game. And just basically changing these numbers until you get 134. 1.35.
Good, close it.
64.6. Well, okay, target, yeah. Now this, I just programmed it so that if the range wound up being within 100 meters of that, it would consider it a hit. But 100 meters is not close enough for a one-ton warhead to destroy any arbitrary target. So this is pretty kind of forgiving as a game. But you saw how much I had to change it in order to hit the target. That tells you something about the difficulty of actually hitting something with something like this. And all I could change is the slew rate that occurred up until it ran out of propellant. Right, and that's about all they had to work with, something like that. Now, another thing that I think is interesting with this is I got some graphs down here that show parameters of the flight as a function of time. This shows the air resistance as a function of time. So horizontal axis is time, and then vertical axis is the air resistance in pounds. Let's see, the X direction resistance is in blue and the Y is in red. So in other words, as it takes off, it speeds up and the air resistance is greater and greater. And I divide that resistance force into the resistance in the horizontal direction and the resistance in the vertical direction, right? So the vertical direction gets higher first because it's going mostly up, but as it goes more and more horizontal, the X direction air resistance goes up. Now it's accelerating all the way towards the engine cutoff when it runs out of propellant. But you can see the drag force drops down before that. Anybody know why that is? In other words, as it accelerates, the air drag increases, but then it drops down even before it stops accelerating. You know why that might be?
Air's thinner?
Yes. It's going up in the atmosphere, and the air is getting thinner.
Wow.
So in this model, I've modeled the atmosphere as having an exponential density, where it's dense towards the surface and then it just decreases in density exponentially, which is approximately how the Earth's atmosphere does. So it drops off, and then it's essentially drifting in a vacuum. So the engine cuts off somewhere around there, and then it's essentially drifting in a vacuum. But then when it comes back into the atmosphere, then there's a lot of drag force. In the vertical direction, it's pushing up now, the opposite direction that it did before. But in the X direction, it's still pushing it against the direction that it. And you can see how much larger the drag force is when it came back into the atmosphere than when it was flying up out. And this is why they were breaking up, because the drag force was, well, you can see it's in the tens of thousands of pounds. This is calculated in a fairly simple way, but it's probably in factor 2 of what it really experienced. So there was a huge amount of force against the front of this rocket when it was coming back into the atmosphere at thousands of miles an hour. And Let me show you a couple of these other graphs. It's kind of interesting. Let me show you the output on here. So for this particular angle, 31.36 degrees per minute, the impact speed is 1,933 miles an hour. So when it gets to the ground, that's how fast it's going. Maximum speed is 3372, and I think that's when just where the engine cut off. But what's kind of neat is the velocity is a function of time, I think, somewhere here. No, here we go. Yeah, this is kind of neat. This is just, its speed is a function of time. So it starts out motionless at takeoff, and then it increases, engine cuts off, and then the velocity drops. Velocity drops down because it's drifting up, right? And then here the velocity is constant because it's moving across the top of its arc. Increases again, but then when it hits the atmosphere, it slows down, right? And then this is actually after impact, so it's not moving. That shouldn't be there. So it's kind of interesting to see, what the flight was like. And this is, probably approximately close to what these flights were really like. So I think I have a copy of this file someplace on my website if anybody's interested in playing this exciting game. Okay, anyway, just want to show you that.
All right. Okay, are there any more questions? I'm going to wrap up here and turn off the archiving. And the sharing. Yeah, let me go ahead and self-archive. Thanks for coming today. I think there are some more events related to World War II going on